Welcome to Module 05. In this lesson, we focus on the final control element, the valve, damper, drive, starter, relay, or stage that converts a BAS command into physical action. A controller can calculate the correct output and still fail to produce the intended result if the actuator does not move, the linkage is broken, the valve lacks authority, the fan is in hand, or the process lacks capacity. The field lesson is simple. Command is not proof. We verify command, position, mechanical movement, process response, and the outcome before we name the cause. After this module, you should be able to separate the different layers of evidence in a control system. A command tells us what the controller requested. Position feedback may tell us what the actuator believes it did. Mechanical movement tells us what actually moved. Process proof tells us whether air, water, pressure, temperature, or capacity changed. We will also review fail-safe behavior, stroke testing, valve and damper authority, drive proof, and alarm wording. The goal is to stop guessing from the screen and start proving what the system actually achieved. The core concept is that a BAS command is only the first link in a chain. The controller commands an output. The actuator may move. The valve stem or damper blade may or may not move with it. The air or water may or may not respond. Finally, the process outcome tells us whether the building received the intended effect. This is why a good sequence distinguishes command, position, proof, and outcome. If those are mixed together on the graphic, the operator may believe the equipment is working when the physical process is not responding. Use this language during troubleshooting. Command is the requested action. Position is the reported or estimated actuator position. Mechanical movement confirms that the shaft, stem, blade, or stage actually moved. Process proof confirms the effect on airflow, water flow, pressure, temperature, current, or another measured outcome. Authority tells us whether the final element can influence the circuit over the needed range. Capacity tells us whether the connected system can actually produce the required result. This vocabulary prevents us from blaming a component too early. This slide gives the evidence ladder. At the bottom is the command written by the BAS. Next is the status or position reported by the device. That still may not prove blade movement or valve stem movement. Then we look for mechanical travel. After that, we look for flow, pressure, current, or another process proof. Finally, we verify the outcome. Did the zone cool? Did the coil transfer heat? Did the fan move air? Did pressure recover? The proof levels should match the consequence. Critical equipment may require several independent indicators. Final control elements include valves, dampers, variable frequency drives, starters, compressor stages, heater stages, relays, and factory interfaces. Each device has different failure modes. A valve can open without water flow. A damper can report position while disconnected blades remain closed. A drive can accept a speed command while local hand mode prevents BAS authority. A starter auxiliary contact can prove electrical state without proving airflow. Do not use one proof strategy everywhere. Match the evidence to the device and to the consequence of failure. Fail-safe behavior describes the physical response under a defined failure, often loss of power or loss of signal. There is no single correct answer for every device. An outdoor air damper may fail closed. A heating valve may fail open for freeze protection. A cooling valve may fail closed to avoid uncontrolled condensation. Some isolation valves may hold last position because sudden movement creates risk. The actuator spring direction, valve body, normal position, signal action, and sequence must all agree. The field requirement is to test the behavior physically, not merely read the submittal. Authority and capacity are different. Authority describes whether the final control element has enough influence over the circuit. An oversized valve, poor pressure relationship, or nonlinear damper can make small movements produce large process changes, or no useful change at all. Capacity describes whether the system can produce the required result. A cooling valve at 100% with warm discharge air may mean warm chilled water, low flow, fouled coil, excessive airflow, or load above design. The controller may be showing demand correctly. The engineer must verify why the physical system cannot deliver. A stroke test can prove the action direction, full travel time, feedback scaling, fail position, linkage, and process response, but it must be planned. Fully opening a steam valve, outdoor air damper, or large water valve may affect occupants or equipment. Use bounded steps when full stroke is not safe. Record the starting condition, the command, the expected response, actual travel, feedback, process evidence, and any delay. Then restore normal operation and document the result. Functional testing turns assumptions into evidence. The common failure is trusting one signal too early. A command does not prove movement. Actuator feedback does not prove flow. A drive running status does not necessarily prove the fan is moving the required air. Another mistake is tuning around mechanical defects, stiction, loose linkage, oversized valves, failed dampers, or manual overrides. The final common error is alarm wording. Do not write an alarm that says cooling valve failed when the logic has only proven insufficient cooling response. Alarm the evidence you have and let the technician investigate the cause. Use a structured diagnostic method. First, verify the command. Who is writing the output and at what priority? Second, verify authority. Is the BAS actually allowed to control the device, or is there a local override, hand mode, priority conflict, or factory control boundary? Third, verify mechanical movement. Fourth, verify process response through flow, pressure, current, temperature, or another independent measurement. Fifth, verify capacity. If the system lacks water temperature, pump flow, fan pressure, or coil capacity, changing software will not fix the physical limitation. Best practice is to make final element evidence visible and repeatable. The sequence should identify device type, signal range, fail position, travel time, feedback type, proof method, and failure response. Trends should include command, feedback, proof, process variable, operating mode, and limiting conditions. Stroke tests should be bounded and documented. Alarms should separate actuator tracking from process response. Finally, asset records matter. Critical valves, dampers, drives, airflow stations, proof switches, and actuators require preventive maintenance just like controllers and servers. This module reinforces a professional controls habit. Do not confuse the screen with the building. Command is intent, position feedback is useful but limited. Mechanical movement does not always prove flow. Process proof tells us whether air, water, pressure, temperature, current, or another meaningful outcome changed. Authority and capacity determine whether the final element can achieve the result. Fail-safe behavior and stroke tests must be documented and physically verified. When a system fails, alarm the evidence you have. Do not name the component unless the sequence has actually proven the component failure. Use this knowledge check to reinforce the difference between evidence and diagnosis. The best answer is C. The BAS has evidence of insufficient cooling response, but it has not proven the exact component cause. The valve may be commanded high and actuator feedback may track, but chilled water temperature, water flow, coil condition, excessive airflow, sensor scaling, and load must still be verified. A professional alarm reports the observed outcome and probable causes. It does not falsely name one failed component when the logic has only proven a failed response.